All right, so welcome back, folks. I want to just let you know that I want to commend you. I just want to start out by commending you folks for being able to hang in there and being able to stay focused through the all the things that have been going on, and being able to continue to try to learn here with me in class here. And so as we finish up our last lecture for the semester, like I said, I want to congratulate you for making it this far, but I also want to commend you. Like I said, I think with all the things that have been going on, you folks have done a tremendous job of staying focused and trying to keep up with the work and doing the work here. Okay? Um, so hopefully I'll get a chance to see some of you folks. Well, I'll see you on Friday. So make sure tomorrow, make sure you come with your questions. I just want to go ahead and finish up with what we're going to have here. I would like to try to get done with the two gas laws that you worked on with the PhET labs, and I want to go ahead and talk about Boyle's law and Gilles-Lach's law. So you'll see those two on the exam next week. And so I want to try to get through that discussion. I may run over a little bit today, or run over just a little bit, but I do want to make sure that I get that covered for you. Okay. All right, so let's go ahead and let's get started. We finished up talking yesterday about pressure. We talked about how what creates gas pressure. Okay, we said then that gas pressure is an observation that we can make. We don't see the gas particles moving. We don't see them colliding with one another, but we see the results of those collisions. And the results of those collisions is measured in pressure here. And so what we did yesterday also then was we were able to talk about how we are able to measure the different units that we can use to describe pressure. What you need to make sure you're able to do, and please practice it, is be able to convert between the different units of pressure. That is something that you'll have to be able to do as we discuss the gas laws today. Okay. All right. So with that said, then the last thing I want to talk about is that I want to talk about the nature of the gas motion. How do gas move? Gas particles move, and so we know that gas particles move. We said then that gas particles move based on the kinetic molecular theory in random, rapid, and constant manner. So gas particles move. And the way they move is in what we refer to as a translational manner, and that is they move from one position and then they move to another position. They don't just stay in one place, that they move from one place to another. Okay? And so what we want to be able to do is we want to talk about what affects that motion. Okay? What affects that motion? We saw then what affects the pressure, because if we can talk about what happens to that motion and what affects that motion and how it's related to heat energy, we can go ahead then and talk about the relationship between pressure and heat as well. Okay. All right. And so with that said, then we saw then that the gas particles move. And what I want to do here is I want to go ahead and finish using this PhET lab to get this done. What I did with the PhET lab then is I've clicked on the third option. Remember, we started out with the ideal here, but there is a third option here that deals with energy. And the reason why I want to talk about energy here is that when we talk about an object in motion, and I mentioned this at the very beginning, okay, any object that's in motion has what we refer to as kinetic energy. So if you take a look on the left-hand side here, this box here, which I dropped down, measures the kinetic energy of a particle versus the number of particles that has that kinetic energy. Kinetic energy, again, is just the energy associated with an object that is in motion. So if you take a look at the graph above this one here, you see then that what we do is we measure the speed of the object, the speed of the particles, and these both here will measure the speed and the energy of the particles, the speed of the particle and the relative number of particles that has that speed. So both of these here, both of these graphs here, which will form when we get when I inject the gas particles into this chamber here. Well, when you look at these two graphs, you're going to see that both of these graphs depict then the motion of those particles. And so what I want you to be able to do is I want you to take a look at how these graphs change here with the changing temperature up here. And again, the temperature here is going to be set in Kelvin, and I'm going to that's for a very specific reason. And when we do the gas laws, you'll see why. Okay. All right. So let's go ahead and do this. Let's go ahead then and let's inject, and I'm going to stick with the heavy particles here. So the heavy particles, there's two different types of gas particles. Remember, we have the heavy, that is the larger, the more massive particles, which are represented by the blue spheres, and the lighter particles that are represented by the red spheres here. Okay, so let's go ahead then and let's punch in 50. So right now we have 50 gas particles here. Again, this is the microscopic level, and this is what we observe here. Okay. All right, so if you notice here, based on the graphs here, you'll notice then that the graph here looks like it's peaking here. So you look like it looks like there's this graph here, that's kind of a curved graph here. Okay, what you'll notice then is that this curved graph, and I'm going to pause it right here. Okay, what you're going to notice is this graph is kind of curved, and I'm going to highlight this for you. Let's go ahead and take a look at what we have here. Okay, we have a graph that is curved in this roughly in this manner right there. Okay, and we have a similar curve right here, and I'll get to that in just a moment. Okay, but we have this curve right here, which means that if you notice this, the greatest number of particles exist right here at the lower speed. So this is lower speed, and the peak here, this peak right here, at this peak of the curve, that represents the maximum number of particles that exist there. So what you need to make sure you keep in mind is that when you read this curve here, everything underneath this curve then represents the number of particles. And so what you want to notice here is at the peak here of this curve, okay, so I kind of rounded it out a little bit. At the peak here, this represents the maximum number of particles. Okay? So if you notice here, the curve is the fattest, the largest underneath this part here. What that means then is that we have then the maximum number of particles that have this particular speed. If you look over here, you have some particles that move faster. So over here, you have a certain number of particles move faster, and over here, you have a certain number of particles move slower. But the average here, so this peak here represents the average number of particles, okay, that possess a particular speed. And so if you notice the same thing kind of holds true here. If you see the peak there, it kind of levels off in this manner here, okay? And the same thing, we have then this peak here, which represents then the average number of particles that have this particular kinetic energy. So I want you to be able to correlate then the speed, how fast the particle is moving, to the amount of energy that it has. Okay. Now there is a formula that relates speed to energy. I don't need to know that, but you see then that both of these graphs are similar to one another. What that is telling us then that is in this particular chamber here, you'll have certain particles that are moving very fast, and I'm going to represent that as an arrow, okay, a long arrow. You have other particles that are not moving as fast, okay, and you have some particles that are moving fairly slow. And the different lengths of the arrows represented how fast or how slow they're moving. However, the majority of the particles then will share a average velocity that's very similar to these here. Okay, so you'll have a few that are move very fast, like we have represented here, a few that are moving very slow, but the majority of them will be moving at an average mid-speed way. Okay, and so that's what the graph is telling us. That is what the graph is depicting for us. Okay, so let's go ahead then and let's continue on. Let's see what happens then when we change some factors. Okay, all right, so let's unpause it. Okay, so there's our gas particles moving. The graph seems to sit right here. Let's take a look at what happens when we add heat energy. Okay, so remember, this represents energy. Okay, either we're adding heat energy or we're going to remove heat energy. So let's go ahead and add heat energy here. What I want you to do then is take a look at what happens to the particles inside the chamber as we increase the temperature. If you notice that we're increasing the temperature up here. Okay, and what happens to the graph? So let's pause it right here. Okay. Let's pause right here. Let's take a look at what happens to the graph then as we continue on. Okay, the graph here, if you notice then, still is kind of that curved graph. It's still that curved graph, but look what happens here. Okay, that curved graph now has shifted. So the average, the peak right here. So if you take a look at the peak, remember in that first one, the peak was over here. The peak now has shifted down over to here. So the speed now has increased in speed. The peak has moved down along the x-axis here. And so what does that mean? It means then that you have more and more particles. So the average number of particles now have a greater speed. By adding heat energy, we've made then most of the particles move faster. Now, just like with the previous graph, we'll still have a few that are moving a whole lot faster than everybody else, a few that are moving a whole lot slower than everyone else, but the majority, and if you take a look at this here, and the white space region, the majority of the gas particles are moving at this higher rate. And so what can we conclude here? As we increase the heat energy, so we added in heat here, as we increase the heat energy, let's go ahead and sum it up here, as we increase the heat energy, okay, the speeds of the particle increase, And what we'll notice here also, that will also lead to an increase in kinetic energy. And that's what we have right there. The relationship between heat energy and kinetic energy. As we increase the heat energy, we increase the kinetic energy of the particles as well. And that is something that make sure you write that down, folks, because that's something that you need to make sure you're absolutely able to do. Okay. All right. So with that said, then you notice here the average speed, and let's take a look up here. The average speed, and I'm sorry, I forgot to draw your attention to this earlier, but the average speed, meaning that the speed of most of the particles has increased to 663. So keep an eye on that as let's unpause this here, and I'm going to add a little bit more heat, and you're going to see then that the average speed is going to increase as well. It goes up to 730. Look at the graph as well. The graph then also shifts, the peak shifts over, but the average speed there is going to increase. So as we add more heat, the speed goes up, the average speed here goes up, which means then the kinetic energy also increases. And that is what you will need to make sure you keep in mind as we move forward with the gas laws. Okay. All right. Very good. Let's go ahead then. And what I'd like to do is let's take a look at then. So we saw then that the pressure here changes with the number of particles. We saw that yesterday. We also saw then, and if you've noticed here, hopefully some of you noticed, I'm unpause it again here, that the pressure also changed with increasing temperature. So we can change it. So the number of particles here didn't change, folks. We started out with 50, we still have 50 now. Okay. So what we see here then is by adding in more heat energy, we get these particles to move faster. We get these particles to move faster. And as they move faster, they have more kinetic energy. And so if you notice here, as they have more kinetic energy, and if they are moving faster, let's go ahead and continue this here. As they increase their kinetic energy, and I'm going to pause it right here just so I can summarize this for you. Okay. Okay. As we increase the kinetic energy by adding more heat, as we increase the kinetic energy by adding more heat, what happens then? We're going to increase the number of collisions. And remember, we talked about this yesterday. If there's any way that we can change the number of collisions, that will lead to an increase in pressure. So an increase in kinetic energy leads to an increase in number of collisions, which then it leads to an increase in pressure. This is how we can explain then why increasing the temperature here, which is, and we saw the temperature increase here, by adding more heat, we increase the temperature. Okay. We know now why the pressure increases, because the kinetic energy of the particles go up because the speed increases, and so they're going to collide with each other more often. And if the number of collisions increase, the pressure also will increase. And that's what I want to draw your attention to, because that's what we'll be focusing on as we talk about these gas laws. We're going to, with these gas laws here, what we're going to be examining then is we're going to be examining the relationship, or what are some of the factors then that will affect the pressure. Okay, so I'm going to go back here to the ideal gas here. I'm going to go back to this here, and we're going to use this then to talk about how what factors affect the gas pressure. Okay. All right, so with that said, then let's go ahead, and I'm going to go ahead and I'm going to click open this here to get, we get number of particles in place. Okay, we have the temperature, we have the gas pressure gauge here. The pressure gauge is 0. Let's go ahead and let's put in 50 particles of the gas. Okay, pressure then increases to about 5.5. Okay, and the temperature there, we have the temperature now because these gas particles are moving. Okay. All right, so we saw then yesterday how by increasing, by putting in more particles, we're going to increase that pressure. That's what's known as Avogadro's law, and we won't worry about that in this lecture here, or in this class for right now. Okay, but what I want to do then is I'm going to go ahead then. In your Fit Lab, you were supposed to click on the ruler here. Okay, and if you notice here, and we talked about this already, by adding this here, what it does for us is it allows us to measure how big we can make this particular box, and how small we can make this particular box. Okay. All right, so that means then we can change the size of the box, which means that we can change the volume. And that's what the First Fit Lab is there to get you to see. Okay, and so let's go ahead and take a look at what happens to the pressure. What I'd like you to do then is take a look at what happens to the pressure when I make the box smaller. So we go from 10 to about 5. Okay. If you notice here, as we made the box smaller, as we decrease the volume of the box, and remember, this is one-dimensional, But remember, volumes is length in 3 dimensions. So we alter one length, one of the dimensions, we will alter the volume. So effectively here, we have changed the volume. And so as we made the volume smaller, so let's go ahead and make our observation here. Okay, so as the volume went down, so let's go ahead and consider this. Okay, as the volume dropped, sorry about this. Okay, as the volume dropped, okay, what happened? The pressure went up. We had an increase in the pressure as a result of a decrease in the volume. Okay, well, let's go ahead and do the reverse. Let's let's pull this out, okay, to about 15. Okay, so now we have increased the volume. Look what happened to the pressure. The pressure went down. Okay, so let's summarize this here, what we've noticed here. So what we see here then, that as we increase the volume, that means we make the volume bigger. What's the result of that? It results in a decrease in the pressure. Okay, and so what we can do here then is we can summarize this relationship here by saying then that in mathematical terms, that the volume, okay, is, and this is proportionality symbol, the one that looks a little bit like a fish, is inversely proportional to the pressure. That the inverse of the pressure is proportional to the volume. This is a statement of Boyle's law. Okay, Boyle's law then, and hopefully you're able to Boyle's law. Sorry, you're able to get this done on your PhET lab. Okay, and be able to see that Boyle's law essentially states then the relationship between pressure and volume. And what we can do then is you can solve for this then using a constant, okay? And you saw then in the table then that if you multiplied the pressure and the volume, okay, if you multiplied the pressure and the volume with the different pressures and volumes that you obtained, you got then a constant. A constant meaning then that the number is the same. Whenever you take the product of one pressure and one volume, you would get the same number. You take the pressure and volume of another pressure, another volume, and you'll see that it also gives you the same number. So when you multiply these two here, you get what's called a constant. Okay, that's the K, what that K stands for. Which means then, if you take two different pressures and volumes and you compare them to one another, what you're going to see then is that the pressure and the volume in both cases have to be the same. And that is the mathematical expression for Boyle's law. And we're going to see in just a moment then that we can use that to help us solve for problems that involve pressure and volume. Okay? All right, but what you need to understand then is what Boyle's law states for us then is that when you change the pressure, you're going to change the volume. How do they change? They change in an inverse manner. And this shows us then how that change occurs. Okay? All right, so what else affects, let's go ahead and save this then. Okay? What else affects then the pressure? Okay, let's go ahead and let's start all over again. Okay, so we have a new set of conditions to work with. Okay. All right, so I'm going to go ahead and I'm going to put in the gas particles again. Okay. This time, though, what I'm going to do is I'm not going to change the volume. We're not going to change the volume. We want to make sure that volume is held constant. Okay. So we're not going to add any more particles. So we want to make sure that the volume doesn't change. Okay. And so that the volume is not the factor that affects the pressure. What we're going to do, though, is we're going to change the temperature. Okay. And so let's go ahead and let's take a look at what happens with the temperature here as we add in more heat. As we add in more heat, we expect then the thermometer here to go up. And so as we add in more heat, okay, let's go ahead and let's continue to add more heat. You look at the temperature, it's going up. So if you notice the temperature, it's going up. Look what happens to the pressure here, folks. So let's increase it to about 845 Kelvin. Look at the pressure here and look what happened. Let's go ahead and write that down really quickly. So as we increase the temperature, by adding in heat, okay, as we increase the temperature, what did that do? That increased the pressure. Okay, so you notice that as the temperature went from 300 Kelvin to from 300 Kelvin up to 845 Kelvin, that means we increased the temperature. The pressure went up. But look what happened to the particles, folks. They're moving faster. And so therefore they have more collisions. Exactly what we just talked about in the previous discussion when we talked about kinetic energy. Okay, so they are colliding more here. If you look at it, they're bouncing all over the place, and they're bouncing more often, and they're bouncing more quickly. And so the pressure goes up. And so we see then that as we increase the temperature, we're going to increase the pressure as well. let's go ahead and do the reverse. Okay, so instead of adding heat to this gas chamber here, let's take away the heat. Okay, so what we're doing here is we are showing the ice. So we are dropping the temperature here. Okay, you can notice here we have decreased the temperature by cooling down the gas. First of all, what do you notice? Gas particles move slower, and as they move slower, they collide less, and then the pressure is going to decrease. And so look what happens here. Let's go ahead and write this down. As we decrease the temperature, as we made the temperature go down, we see then a drop in the pressure. Okay, so how can we summarize that? How can we summarize this relationship? Well, as the temperature, so let's go ahead and do this. The temperature then changes in the same way as the pressure. So there is a direct relationship, not an inverse, but a direct relationship between the two of them. Okay, and so we can relate then these two together. Okay, and so this is the second FET lab that you do. You saw then that when you took the quotient, when you divided these two here, okay, you saw then that when you do, instead of multiplying these two together, you divide the two, you get your constant. Okay, and so when you take the pressure and temperature under two different conditions, and you take the ratio of the two, that is, you divide the two, they should then be equal to one another. And this then, folks, is what we refer to as Gay-Lussac's law. Okay, and that is the second FET lab that you were asked to do. Okay, and so now what we did is we took two factors. We changed the volume of a gas, we changed the temperature of the gas, and we saw then that changing those affects the gas pressure. Okay, and so the relationship between volume and temperature is summarized in Boyle's law. The relationship between pressure and temperature is summed up in Gay-Lussac's law. Okay, and so we were able to see, using this FET lab here, then we're able to see then how on a microscopic scale those factors affect one another. Okay, all right. So what I'd like to do then is let's go ahead and let's close up this FET lab here. Okay, and what I'd like to do then is let's go ahead and let's take a look at the a couple problems involving Boyle's law and Gay-Lussac's law, and I'm going to work out a couple of those with you. Okay, and then we'll be finished. We'll finish up with this. Okay, so let me go ahead and change this up. Okay. Okay. All right, and so let's take a look at a few of these gas laws here. Okay, so we talked about Boyle's law here. There is Boyle's law. Okay. So Boyle's law then allows us, and like I said, when you take the pressure and the volume and you multiply them together, okay, it allows us to work out and solve for the pressure of the volume in another set of conditions. Okay, and so let's take a look at an example of a problem here where we will have to apply Boyle's law. The method that you're going to use to solve for these problems then will involve then, first of all, identifying what you're given. Okay, so what you want to make sure you do is identify what you're given first. Okay, so let's go ahead and let's identify what we're given. Okay, so how do you do that? Look for the measurements, folks. So we have here volume. How do we know? The units. So we have a volume here. We have another measurement here, 103 kilopascals. What is this measurement referring to? It's referring to a pressure. Okay, how do we know that it's a pressure? The unit, kilopascals. Okay, all right, and then we have a third one here. We have another measurement here, kilopascals as well, so that's a pressure. So what is given to us? We are given a volume of 30 liters, and we're given two pressures. One that is 103 kilopascals, and a second that is 25.0 kilopascals. So the very first thing you should do, identify all of the values that are given to you. Okay. Then what you want to do next is ask yourself, what is the problem asking you to solve for? Okay, so when you take a look at this, you got to read it. Okay, if you read it here, it's asking you about a volume. Okay, so they're asking you to solve for a volume. So in this particular problem, they give you a volume, they give you two pressures, and they're asking you to solve for a volume. Okay, and so with that said, then the third question you should ask yourself as you solve these problems then is, what equation relates these factors together? Well, so far, we only have two equations, okay? So Boyle's law has pressure and volume in it. Gay-Lussac's law is pressure and temperature. So the equation that we're going to use then is the Boyle's law equation, which is P1 equals V1, P2 equals P2, okay? And so this is the formula that we're going to use to solve for this volume here. But now what you have to do then is you have to identify then which volume is V1, which is V2, and therefore which is P1 and which is P2. Here is where you have to go back and you have to read it and be careful. Okay, so let's go and read this here. We were told that we have a balloon. We have a balloon that was initially at 30 liters, and at that 30 liters, it had this pressure. Then what they do is they change the pressure to 25 kilopascals because the balloon goes up in altitude, and so they're asking us to find the new volume, which means then, folks, this is the pressure, the initial pressure, P1. That's what we start out with, and that's what it changes into. Okay, and this is the volume for this pressure. That must be V1. So we are solving for V2. Okay, all right. So that's what you have to be able to do as well. So once you have that identified, let's go ahead then. What I always suggest you do is rearrange this equation to isolate for the variable that you're solving for. Okay, so let's go ahead and do that. Okay, we're going to solve for V2, which means then we're going to divide both sides by P2, which gives us then P1 V1 over P2. And there it is. That's from this formula, we have derived now an equation that we can use to solve for our unknown. Okay. The last step then is just go ahead and take these values and plug them in. Okay, let's go ahead then, let's plug it in. So let's solve for it. V2 then is going to be equal to P1 times V1 over P2. Let's plug in these values here. P1 then is 103 kilopascals. Okay. V1 then is 30 liters. Okay, so let's go ahead and plug that in. 30.0 liters. And then all over P2, which is 25 kilopascals. Okay. All right, so you plug that into your calculator, and you should be able to get a value then of 124 liters. Okay. All right. So that's how simple doing these Boyle's Law problems are, folks. You need to make sure you just practice them. I'm not going to sign up for homework, but make sure you practice it tonight. Find the Boyle's Law problems and practice them, okay? And then make sure if you have questions about it, make sure you come by and see me and get that extra. But what I'd like to do then is take a look at number 13 here from the chapter 14 problem set, and take about 2 minutes to work out this problem here. Take about 2 minutes to work out this problem here, and then we'll go over it together. Follow the steps that I pointed out to you. Ask the 3 questions. Identify what's given. Identify what they're asking you to solve for. Identify the correct formula that you're going to use, okay? And then go ahead and set about solving for it. So take about 2 minutes, work out this problem. All right, let's go ahead then and let's identify what we're given. So what I would suggest you do is you don't have to write out the questions, but either you are writing out what they're given to you or you're doing it in your head. I'm going to go ahead and write it out. Okay, so here we have then a volume by the unit here. Okay, we have a pressure here, and then we have another pressure right here. So we are given then, I'm just going to write this out, we are given a volume of 22.50 liters. We're given a pressure of 105 kilopascals, and we're given another pressure of 40.5 kilopascals. Okay, so those are all what we're given. Let's take a look at what they're asking to solve for. So if you take a look at this here, if you take a look at this, they're asking us to find then what the new volume would be. So they're asking us to solve for volume, folks. Okay, so we were asked to solve for volume. All right. So which one of those gas laws has pressure and volume in it? Well, it's going to be the Boyle's law. So let's go ahead and write that out. So P1 V1 equals P2 V2. So there it is. That has the pressures and the volume in it. Okay. All right. So with that said, then we have to identify which of these pressures is P1, which is P2, and which of these volumes is V1, and which is V2. Okay. So here we have a volume to start out with at this pressure. And we're told that the pressure changes to this one. This must be the initial P1, and it changes to P2. This is the volume then that's associated with the initial P1, so that must be V1. And so in the end, then we are solving for V2. So this problem is identical to the one that we just did. Okay, so let's go ahead then. We're solving for V2 here. So let's take this gas law here and let's rearrange it to solve for V2. That means that we're going to divide both sides by P2. It's going to be P1, V1 divided by P2. Okay, and so there it is. We have everything we need in order to solve for this particular problem here. Okay, so let's go ahead and let's plug in our values. Let's plug in our values and let's see what we get. So V2 then is going to be equal to P1, 105 kilopascals, times V1, which is 2.50 liters, okay, all over P2, which is going to be 6.5 kilopascals. Okay? So you plug those numbers in your calculator, and you're going to get your final answer then as being 6.48 liters. Okay. All right. All right. So I am out of time here. I've gone quite a bit over. And so what we'll do here is this, folks. Okay? For the exam, and I'll repeat this again for you. So we're going to stop right here. Remember, on the exam, you're only held accountable for what we do here in lecture. Okay? So what we'll do then is on the exam next week, you will only be held accountable for doing a calculation involving Boyle's law and no other gas laws, but be able to describe the relationships that are given to you in Boyle's law and in Gillisak's law. Okay? To be able to describe how pressure is affected by volume and how pressure is affected by temperature. Okay? And to be able to use Boyle's law to do these calculations here. You will not be asked to do any calculations involving Gillisak's law, but be able to, with Gillisak's law, be able to describe the relationship between pressure and temperature. Okay. All right. So with that said, then I'll make that point clear to you. I'll repeat that point again to you tomorrow. Okay, when we review. So please make sure you come to class tomorrow, and we're going to meet in Zoom. And so same Zoom info for Monday. We're going to use that same Zoom info to meet on tomorrow. And then at that point, then please make sure you ask your questions. But do try more of these Boyle's law problems. You can get to some sample practice problems from the PhET lab itself. If you want to do some of the practice problems from the Gillisak's for Gillisak's law, go ahead and do so. There are some problems on the back of that PhET lab as well. And if you need help with those, make sure you come by and you ask. Make sure you ask those tomorrow. Okay. All right. So with that said, let's be done with this, and I look forward to seeing you folks tomorrow. Please make sure you get your questions ready to ask for tomorrow. Okay. All right, folks. Have a good day, and I will see you tomorrow.